All right, howdy everybody. In this video, what we're going to do is go over the mechanism of the Baylis-Hillman reaction. This would be an advanced mechanism, and even though it's a named reaction that does not appear in a number of organic 1, organic 2 reactions, the elementary steps and the principal components of this reaction are things that are often covered in the sections on ketones, particularly alpha-beta unsaturated ketones. And that is okay, even though that we're going to actually use an ester for this reaction. Most of the time, these kinds of conjugate additions and aldol type attacks are covered in the ketone section. A couple of notes for those of you that are enjoying the Professor Carbon channel. I'll remind you that we do appreciate subscriptions on YouTube, so please do subscribe to the Professor Carbon channel. Secondly, for those of you that are looking for a way to organize the videos, what I'll point out is if you go to our Professor Carbon channel and look for the playlists, we actually have them organized by 2 different ways. So you should be able to find a playlist that's organized by the functional group or the chapter, but you should also be able to find a playlist that's organized by the reaction type. So if you just want practice on arrow pushing mechanisms, there should be an arrow pushing mechanism channel. Okay, as with all of these videos, what I encourage you to do is actually to pause the video and see if you can work this out on your own, and then come back and watch the rest of the video after you've made a really good effort to try to work through the problem. And the reason for that is that's your best opportunity for learning, is to actually work through the problem all on your own. So please do pause the video right now. All right, coming on back. Like for most of these mechanisms, what I like to do is try to identify what bonds are going to be made or broken in the starting materials and in the products. And if I look here at the starting material, there is an H at that position, and there's not an H at this position. Furthermore, we're going to need to generate that carbon-carbon bond between those components, and presumably this phenyl will come from the phenyl over here in benzaldehyde, and that means we're also going to have to break that carbon-carbon double bond. All right, and so, you know, if you think about this, this is really an alpha functionalization, and it's very similar to an alpha functionalization that we've seen a lot of in the Aldol reaction, and that is often we've been able to take these carbonyls at the alpha position here and have some base to do that deprotonation to make an enolate or enolate-like intermediate. In this case, it's the enolate derived from an ester, which is technically has a different name, but we're just going to label it enolate to keep life simple. And then this enolate can attack aldehydes. And we've seen this a lot of times in our aldol reactions. Oops, and initially you get O-, and of course after it's protonated, after the workup, it ends up being OH. Okay, so that's a fairly standard sequence. The hiccup here is that this H in question is on an sp2 hybridized carbon. To put that a different way, it's part of a alpha-beta unsaturated ester. And if you've watched our other videos on the Professor Carbon channel on identifying acidic alpha H's, and so that's under the ketone playlist if you're interested, I pointed out that this is not an acidic H, and so we cannot directly deprotonate there. So I'm just going to put this, draw it out so we all know what I'm talking about. And if we have a base to do this deprotonation, we would make this vinyl anion. And it turns out this position has a very high pKa, and we're not going to do that step. And the reason we're not going to do that step is, remember, one of the key things that make alpha-beta unsaturated carbonyls special is that they have all these p orbitals lined up. And that's the same p orbital that we like to invoke for these enolates. And so if I just draw out this enolate in a slightly different manner, I would have the O atom, and actually let me just draw that a little bit more sideways so we can put the orbitals in there. So if I have O- out here, that's going to be lined up with the enolate position, and that's going to allow me to have this resonance steps that we've invoked. So over here we used resonance to push those electrons up onto the oxygen, and over here we're going to use that O- to reform that carbonyl. And so that means all those p orbitals need to be aligned to make that happen. And in this vinyl system, the double bond p orbitals are already lined up with the carbonyl orbitals. And so that means if we add in that negative charge, it's going to have to be orthogonal to that system. And it's strictly speaking going to be part of the sp2 underlying framework. And so it's not going to be able to be delocalized. And that really increases the pKa of that site. And it means often we're not going to deprotonate here. Actually, there's very few, if any, reactions I'm aware of that deprotonate that vinyl or sp2 hybridized CH bond next to the carbonyl. So it's really important if we're making enolates that this alpha position be sp3 hybridized, not sp2 hybridized. Okay, so that being said, that's probably the #1 most common pitfall I see in students that try to draw a mechanism for the Baylis-Hillman reaction is they try to use the PPH3 as a base and just directly deprotonate that CH bond. Unfortunately, it's not a viable mechanistic pathway. So we have to do something else to complete this mechanism, and the something else we're going to do is use PPH3 as a nucleophile. And it's a relatively weak nucleophile, but it's a strong enough nucleophile to promote this reaction. And what's really unusual here is we have really 3 different electrophilic sites on these starting materials, and so I'm just going to circle those in green. So the first one here is that a strong nucleophile, of course, can attack the ester, and that would promote acyl substitution chemistry, addition elimination, and we might hydrolyze the ester that way. All these alpha-beta unsaturated carbonyl compounds can be susceptible to addition at the 4 position, and so these are our Michael additions or conjugate additions, things that we might engage with either the Michael reaction or cuprate additions or those sorts of things. And our aldehyde here is also actually going to be electrophilic, and so we have a lot of electrophiles in these starting materials. And so PPH3 is going to be a nucleophile to complement that. And what's really special about PPH3 is it's going to attack selectively over here at the distal position. And so just so we can keep the page clean here, I'm just going to redraw everything down below. So if I have my methyl acrylate PPH3, got this lone pair, and it's going to come and do a attack, and we're going to make an enolate then from this. And one thing that is really important to remember is anytime in these mechanisms that we generate a negative charge, we also want to put a positive charge in place. And in this case, it's going to go on phosphorus. And by the way, these kinds of phosphonium salts are analogous to what you might use in the Wittig reaction. So I would encourage you to watch our videos describing the Wittig reaction and some syntheses that utilize the Wittig reaction as well, or look that up in whatever textbook you're using. Okay, this enolate now, and as a reminder, anytime we draw one of these classic intermediates, I always encourage you to label them. It'll help train you to recognize the similarities between these functional groups. And again, often students that try to memorize organic chemistry, especially the second semester organic chemistry, really have some problems because we keep putting so much more stuff layered on top that it becomes almost impossible to memorize. But if you can recognize the patterns, then you can have an approach to solve it. And one of the underlying patterns is that we have a lot of the same kind of steps that reoccur over and over again. And you can start to recognize that if you actually label the intermediates for yourself. So we're going to label this one as an enolate. The next thing we can do now is the enolate is a nucleophile, and it's a strong nucleophile, and it's one that we've seen before engage in the aldol reaction. And so what we're going to do now is do exactly that and have what looks like an aldol attack. And this now generates that key bond that we need in our product. And you'll notice we've done it through an enolate, which is similar to the first reaction I showed above here. And so it's the same kind of enolate that we have, not this. And so that's very important. All right, so this kind of enolate then still has this dangling ppH3 coming off, and it's still plus, so we still have a minus, and so we still need that plus there. Now, the next step of this is going to be an elimination reaction, and technically this would be what we sometimes refer to as an E1CB mechanism, which is a lot of jargon. What I like to say is the enolate is going to push off the leaving group. And so much like in the aldol reaction, we're going to use this anion here to deprotonate the starting material, and we're going to reform an enolate. And realistically, this deprotonation is probably intermolecular, so there's not really a great orientation for that O- to grab the H+ that's right next door to it. The orbitals don't quite line up. But as a reminder, it's really difficult to ever do a reaction on exactly one molecule. We do chemistry, especially organic synthesis, on Avogadro's number of molecules. So there's a lot of molecules, even in a very, very small sample. And so often these deprotonations are, a neighboring molecule that gets deprotonated or a solvent molecule. I'm just drawing it here intramolecularly to make the mechanism a little bit simpler. All right, so there's our OH. We're going to have our O- here now in our enolate again. And so let's just follow my advice and label this one more time. And now we can start to see some of why it was very important to start with ppH3. Because we can take this enolate and we can imagine pushing it down through the red arrows here and kicking off ppH3, and that would generate the products. So that's going to be the correct way to go here. And that regenerates our double bond there. That was in the starting material. The other thing that we could consider, by the way, is if we take this exact same arrow and this exact same pair of electrons, but instead we kick off OH minus. That would lead to a different product, a different alpha beta unsaturated ester, and we'd have to lose hydroxide. And so the same enolate has to then choose whether to kick off the ppH3 or the OH. And so being a ppH3 plus a cation means we're going to lose a neutral ppH3 molecule, and that's going to make the ppH3 plus a better leaving group, and so that'll lead to that chemoselectivity. It's one of the ways that it differs from the standard aldol condensation, where in the aldol condensation we kick off OH minus. So that's still an option here, but we've made the leaving group a better leaving group by making it positively charged in the form of the ppH3 plus. Okay, so the other thing that I'll point out is that it's probably actually important to draw this enolate, and I would discourage anybody from drawing this just simply as an E2 reaction. So we could imagine doing the elimination directly from here. This is another common mistake that I see as students just want to do the elimination from this intermediate. But if we did that, I mean, there's not technically anything wrong with the arrows. There's still all the right electrons going in all the right spots. But remember, our E2 reaction has some very specific stereoelectronic requirements. And so if it's an E2 reaction, it has to have that anti-periplanar arrangement where the H is lined up opposite the leaving group and the base is going to come in and it's all going to happen at once. That stereochemistry sometimes can be quite significant. And what's nice about going through the enolate and showing that enolate again is that we're showing kind of the special reactivity of our substrate, because this H here is going to be much more acidic than your average H in an E2 reaction. And because we're pushing off the leaving group from the enolate, we get around the requirement for this anti-periplanar relationship that's required for the E2 reaction. And so I would encourage you, even though that there's nothing technically wrong with this arrow pushing to go directly to the product, it doesn't quite reflect or capture fully the reactivity of the starting material. So I'd encourage you to go through the enolate and draw that extra step. All right, so that sums up this mechanism. What I'll encourage you to do if you're enjoying these videos or if you're finding them helpful is please do subscribe to our YouTube channel. That's very important. A little bit of information that really provides us encouragement to keep making these videos and expanding the number of problems that are available on Professor Carbon. As I pointed out at the beginning, please do go to the playlist that interests you the most. So if you're interested in more arrow pushing mechanisms, go to that playlist. If you're looking to study more about ketones, please go to that playlist. Lastly, if you'd like access to these PDF files, either in the blank format before they're filled out or in the complete format after they're filled out, you can access those from our Patreon page by becoming a subscriber. So we'd appreciate that as well. Thank you. Please watch the next video and share with a friend.